Welcome to what I promise will be the final and probably brief video in this lecture series on data structures. All the data structures we've discussed so far have been built-in Python data structures, meaning they are always available no matter what. However, Python is a modular programming language, meaning it's very easy to bring in new objects, functions, or things from other libraries of code written in Python. One such library is collections, which allows us access to some additional containers that expand on top of some of the built-in data structures we've already discussed. Collections is a library that's part of the Python standard library. The Python standard library is a set of packages that are available with almost every Python distribution, regardless of where you get it from. It's sort of the minimal set of packages that ship with Python. We can see what's included in the Python standard library by just searching for Python standard library. We can go to the official Python documentation, and we can see that there are these various packages or libraries such as string, RE, readline, datetime, calendar, array, random, math. We can see that these libraries add a lot of additional functionality that's not contained within the built-in Python data types and operations. For example, we might import the math module so we can take square roots of numbers. Imports bring in other files containing Python code and add that Python code to our environment so we can use it. It adds this code to what's called a namespace. The namespace is the set of meaningful names in our environment and the way in which they are organized hierarchically. Note that there is a square root that lives in the math namespace. Math lives in our global namespace, our global environment. So there's a kind of hierarchy of namespaces that we can build up to keep names organized in our environment as we're writing our programs. We'll revisit this idea of namespaces in the future. But for now, it's sufficient to know that we can augment our environment with additional Python code by importing packages, modules, and libraries. For the subsequent examples of these containers, we'll be importing these things from the collections module. The first one we'll consider is the named tuple. A named tuple somewhat combines the idea of a tuple with the idea of a dictionary. Tuples, remember, are ordered, and we access information in them based on position. However, they're also immutable. None of the other data structures that we've learned about today are immutable. So if we want to be able to access the contents of a tuple by some kind of meaningful label or name, we might want to use a named tuple. Named tuples are also related to classes. Because we have this verbose equals true keyword activated, Python shows us the class it's constructing to make our named tuple. We don't have to worry about all this code right now, but we might come back to this example in the future after we talk about class definitions. We used the name tuple to create a new kind of object, vector3, a three-dimensional vector which has an x, a y, and a z component. The name of the type of object is the first element of the name tuple, while the second element are the different attributes we would like for it to have. We can now create vector3 objects by calling vector3 and passing in the different elements of our named tuple. We can then access these elements by using this dot syntax, which is known as attribute syntax. In a previous lecture, I had shown you the dir function, which can be used for looking up the methods of a object. I mentioned that not everything in this list is a method. Some of them are attributes. Attributes are properties or variables contained within an object. For all intents and purposes, vec here is essentially a tuple. But we're able to access the elements of this vector by name through its attributes. We'll revisit this idea in the future, since it's a little bit difficult right now to appreciate why we might want something like this. Note that since this object is based upon tuples, we still cannot mutate it. It is immutable. So we cannot reassign the x component of our vector to have some new value. It also functions like a tuple when passed into a function. Here we have a function which accepts three arguments, a, b, and c. And its function is to simply print out those three elements. Here, we call the function and pass it vec as an argument. This asterisk has the effect of unpacking vec into the three arguments shown here. Next, we'll talk about the dec, or DQ. I'm not sure how this is usually pronounced, but it's a double-ended queue. A double-ended queue is similar to queues or stacks, which are abstract data types. You can read more about abstract data types in the book that I mentioned in the previous lecture, Problem Solving with Algorithms and Data Structures Using Python. We can see under the Basic Data Structures chapter, there's a section on stacks as well as queues. A queue is simply essentially a list that's optimized for adding and removing elements from the ends of the structure. Lists are not optimized in this way and will generally take longer to perform operations to add or remove elements from the front of the list. While there's only very specific situations in which this optimization will matter, we can demonstrate that the double-ended queue is more efficient at insertion and removal at the beginning of the container by timing the amount of time it takes to add 40,000 numbers to the beginning of a list compared to the amount of time it takes to add the same amount of numbers to the beginning of a double-ended queue. First, we'll time the insertion for the list. Here we've used what's called IPython magic to do the timing. Anytime you see a cell that begins with a single or double percent sign, that means that this cell is quote-unquote magic, and there will be some extra functionality added to this cell when it's run. Now let's time inserting the numbers for the double-ended queue. We can see that the double-ended queue was roughly 100 times faster inserting the elements at the beginning of the container than the list was. However, it still contains the same values. We can check this by constructing a list and a double-ended queue containing the first 40,000 numbers, and then check that check that a list constructed out of the double-ended queue is the same as the list we just made. And we get true returned from this comparison. Again, while this is only important for some specialized tasks, a 100-fold speedup can be very significant. A counter is a special kind of dictionary that is useful for counting the elements of another data structure. For example, we might have a list containing some set of elements. If we want to count how many of each element appears in the list, we can construct a counter from that data structure. We see when we print the counter that we get back something like a dictionary. In addition to the dictionary-like object and the simple syntax for performing counts of elements of other data structures, the counter also has some helper methods for retrieving elements with the, for instance, highest count. So the two most common elements in our original list are B with a count of 3 and A with a count of 2. We can also access elements of the counter dictionary just like we would any other dictionary. However, counter has the extra feature that if we try to access the dictionary at a key that doesn't exist, it defaults to the value 0, since we have not counted any elements at that key. This is similar to a default dict. A default dict is a dictionary where we can set some default value to be returned whenever we try to access the dictionary at a key that does not exist. Therefore, we could, for instance, have replicate the function of a counter in the following way. We'll define a count dictionary, or a count function. If we wanted to do this with a regular dictionary, we could define a count function where we construct a dictionary, and for each element in the container X, we first check if the element is in the dictionary. We don't need this keys here. If it's already in it, then we increment the count by 1. Otherwise, we have to initialize a new key value pair in the dictionary. Finally, we can return the count dict. So here we've written a function to construct a dictionary with the counts of the elements of that list we had earlier. Using a default dict, the code is slightly simpler. We construct a default dict with an integer default value. This default dict will, by default, return 0 if we try to access it at a key that doesn't yet exist. This way, we don't need to do any checking to make sure that a key is already in the dictionary before trying to increment the count. If we encounter a new letter, then the dictionary will increment from 0. And we see when we run this, we get approximately the same result, except now we have a default dict instead of a regular dictionary. This replicates the function of a counter dict. If you're going to be performing counts, you should use the counter. But there are many situations in which a default dict is useful for things other than counting. Again, there are some topics that we've made use of in this notebook, like the map function, that we haven't really discussed in detail, but that you may want to look up independently. Finally, you should consider some of the following questions after the lecture. One data type, similar to the containers we've looked at in this series of lecture, are strings, which are strings of individual characters. Strings are almost like lists in a way, in that, it's just an ordered collection of individual characters. However, they are homogeneous in that they are all characters, or text, and we don't know whether they're immutable or not. So consider the following questions. Are strings immutable? Are strings ordered? And can we slice strings, as we did with lists and tuples? That concludes the first week of lecture for Unit 1 of the Introduction to Data Science module. I will upload the videos for week 2 prior to next week. Oh, one more thing. Sorry. Now that we have a good understanding of data structures and basic programming fundamentals, we should begin trying to complete our week 1 assignments. The first assignment I mentioned in the introductory video, which is the INMini project, which is a simple mini project in which you create a list and create a function to learn how the grader works for the assignments. Make sure when you're completing this assignment, or any assignment, that you import the grader by running this cell at the top of the notebook before you attempt to use the grader to score any problems. In addition to the INMini project, you should get started on the IPMini project. The IPMini project is a series of mathematical challenges to implement some functions and create some data structures for calculating prime numbers and testing if numbers are prime. So you should work through these questions as well once you've watched these lecture videos.